Hi, my name's Andrew McLaren. I'm going to help you with the non-ideal gas law. A lot of students look at the formula and their brains just kind of hurt. Luckily for you, on the AP exam, that is not included in your list of formulas that you have to work with. It's more of a conceptual question. And I'm going to help you understand how to get points in these questions without fully understanding everything that's going on here, because most students don't in the AP exam. The main thing is that these have opposite effects. So the attractive force of the molecules on each other has one effect, whereas the molecules actually taking up some space, meaning there's less space for movement, has a different effect. So we've summarized those right here. The attractive forces, those cause these deviations where pressure is lower or volume is lower, and the one with the particle volume causes pressure to be higher or the volume to be higher. We're going to look at this in the context of two AP Chem example questions, but you can also kind of see that under low pressure, the effect is one way, and under higher pressure, the effect is the other way. So this Z factor is just a way of us comparing the volume that you might expect to the volume that we actually see if we were to use the ideal gas law versus actual observations. So in some cases, that volume's a little bit too low. In some cases, it's a little bit too high. And in the medium case, they kind of cancel out. These two effects cancel out. And so you do see ideal gas behaviors for most gases for like medium range pressures, or the variations not that significant. So we have two different AP Chem questions here. In the 2019 question, you can see that part D here, the explanation can only be about this attractive force, because we have this attractive force coming into play. The pressure is less than the pressure predicted by the ideal gas law, so the volume explanation just does not make sense. You don't have to do a lot. This is just like a short sentence saying the attractive forces result in this lower pressure. And people got points taken off if they tried to cite both the attractive forces and the non-negligible volume. Now those both are probably present, but one effect is being seen more than the other in this situation. Some students had some other things that they did incorrectly. This is from the chief reader report. This is kind of a summary of it. And this is like stuff that people did wrong that kind of lost them points. So that's the main idea, is don't just state both of these things, because you're going to lose points in doing that. You need to know that when one is going to be having the effect versus the other, in terms of one causing a lower pressure, one causing a higher pressure. That's what we're seeing here. So the pressure was lower than expected, so attractive forces is the appropriate answer there. And then in 2021, you can see we have a similar sort of thing here. We're assuming that these ideal gas laws have no interparticle attraction. This has a bit more of an explanation going to it, but now that we're talking about the volume, so the volume is decreasing due to that that effect. So it's either going to be talking about the pressure being different or the volume being different. In this case, we were talking about that attractive force and how it's going to end up having an effect on either one of those two factors. Now, I haven't seen any FRQs asking about the molecular volume and how that would have an effect, but it's just the opposite. So this was really interesting to me. Only half of students even attempt this question, and only about a third actually earned credit. So those who attempted it, a good chunk of them did not get points for this, and a lot of people don't even try. All you really need to do for a lot of these questions is state which deviation it is, and that's probably going to get you points. It's a flip of a coin. It's relatively difficult to explain, but you should absolutely fill points. This is not the SAT or something like that where you might lose points for an incorrect answer. Like, go ahead and put something down at the very least. And so if you were to describe what's going on, the main idea here is that some conditions are going to cause the attraction forces to be significant. So at lower temperatures, those attractive forces are significant. Things are moving a little bit slower, and they're going to have more time passing by each other, so they're going to get sucked in. If you have things being in a high pressure environment or like low volume, suddenly them taking up like 1,000th or 100th of the total volume, it becomes significant as that volume decreases. So the molecule's volume is more of an effect in a smaller volume environment, which is really high pressure environments. You might think in the AP Chem course description, they're talking about things that are resulting in condensation. That's low temperature. You might think high pressure, well, that's going to cause things to condense possibly. But the bigger effect at high pressures is the particles volume, because now they're taking up significant amounts of space. So these things might both go up in terms of their effect at higher pressures, but the volume's effect is bigger at those higher pressures. So they have opposite effects. Just keep that in mind, and that should help you in terms of like, well, which way is it going? Okay, it's this statement, and then you may have to do a bit of reasoning to explain why this is bigger, but you're probably going to be fine just stating, oh, it's the attractive forces, or it's the mass volume or the molecular volume.